revision week. Of course, um, the exam one is actually coming up. Okay, so today I'm just going to show you because what we're going to do, I'm going to review or practice questions with you today and Wednesdays as well. Okay, so I'm actually calling this part A, but let me tell you in general, these are the areas exam one we actually come from, and I need you to revise on this. In this class, I walk you through to explain or predict, and you remember in part of the assignment, focus on, where I gave some problems, and I asked you to actually decide which one requires to explain, which one requires to predict. So I'm going to make sure, or I think my TA has posted our assignment solution, so you can actually check that. So there's going to be a question on that was centered on explain or predict, just like the way I gave you before in assignment, where they're going to give you scenarios, questions, and they're going to ask you to, what is the intention here? Is the intention to explain or intention to predict? Now, another question we centered on, you're going to be given some functions, and they're going to ask you to decide whether they are convex or concave. We've done that in this class, and I've given you as assignment. So I think what I'm expecting from you, depending on the way question is asked, you're going to make use of first condition, the gradient, and the second order condition. Okay, I think I gave you that as assignment as well. I wanted to revisit that. You remember when you get Asian matrix, right? And the diagonal of the Asian matrix, if they are positive, that would be, if they are strictly positive, that would be a positive deviate. A positive deviate is an indication of a convex function, and there's possibility one of the values in the diagonal of the Asian matrix may be positive, and the other one is 0. That's a semi-positive deviate. For semi-positive deviate, you expect that could be, is convex but not strictly convex. But situation where you have, one is negative and one is positive. I'm just talking about 2 by 2 now. Maybe you have a 2 by 2 Asian matrix. I'm talking about the diagonal. When one is positive, the other one is negative. It is neither concave or not convex, so you can't really decide. And if they are negative, okay, that's a negative deviate. A negative deviate is not a convex. So I think so you need to focus on that too. Then there's something that I call triangular inequality. Okay, there's a rule of convex as well. So I'm going to walk you through that, on Wednesday, which of course we've already done that. And let me say this. If you see what is on the board about clustering, those are the two areas that will feature in this exam. The density base and the Gaussian, it is neither concave or not convex, so you can't really decide. And if they are negative, okay, that's a negative deviate. A negative deviate is not a convex. So I think so you need to focus on that too. Then there's something that I call triangular inequality. Okay, there's a rule of convex as well. So I'm going to walk you through that, on Wednesday, which of course we've already done that. And let me say this. If you see what is on the board about clustering, Those are the two areas that will feature in this exam: the density base and the Gaussian mixture model. Only two of them will feature in this exam. Now, I changed my mind. There's not going to be R, because I said, what is the point? You've been doing R as assignments, and when you come, maybe we're going to spend 1 hour, and there's possibility network, or maybe your laptop is not charged. I don't want to base your performance on that. Does that make sense? So that's why I'm moving away. I changed my mind during the weekend, because when I want to give my student exam, four of us sit down on my own, like, under this condition, does it really make sense? If I put R, it doesn't make sense. What if there's a technological issue? That's not your fault. And that's how I say, okay, what we're going to do, we're going to move away from R. So let R be, what is that? Somebody want to speak with me? I think I'm hearing a background noise. Okay. So, and I said, oh, is it from me? So, and I said, there's not going to be R. So you don't need to worry about your laptop. Come to the exam with your writing material, and you need something very crucial. You know that? Calculator. Scientific calculator. Okay. So the density-based clustering algorithm and the Gaussian mixture model-based clustering. But you know what? Because of the fact that we're not going to use R, okay, under the Gaussian mixture model, we're only going to have two overlapping Gaussian distribution, like two clusters. And you know what? The material, what I posted today, if you check Canvas, okay, is actually going to be pattern of the exam, okay? Even though I'm still going to update that today with question on explain or to let me just say this. The one I release, does not include to explain or predict, right? And does not involve the triangular inequality of proving converse. That is the only one missing. I needed to revise on that. But you know what? I'm actually going to start today from the Gaussian mixture model. How do we do it manually? Okay? It's easy. I want everybody to score 100%. Very easy. What I will advise you to do, spend a lot of time on the material that I provided. So because of that, I'm actually going to start from, please, I need you to pay attention. I'm going to start from this. Look at this question. There's going to be a question like this in exam. Suppose you are given one-dimensional data point. 1, 2, 2, 5, 5, 6, 7. One-dimensional. Okay, just one, because if it's more than one-dimensional, it doesn't make sense computing it manually. We need R. I was looking for a way to escape R in this exam. That was why I came up with this. Now, you know what I want to do today? I'll walk you through how do we do this. And this will give you an opportunity for you to be able to know what is behind the scene when you make use of R. Now, assuming the data can be modeled using a Gaussian mixture model with two components, you know what? The only difference between what I'm going to present now and what you're going to see in exam for Gaussian mixture model is just different data sets. I don't know whether you are getting me. Is everybody getting me? Okay, please be focused. Now, where the initial parameters. Now, take a look at this. You give it the initial parameters to be that. You give it the initial parameter to be that. Don't forget, because I have two clusters, there will be two means, there will be two variances, there will be two missing coefficients. You're going to be given that. Does that make sense? For two parameters. Why? Can somebody tell me? Why is it that we do not have variance, covariance? Why is it that we don't have covariance? Why do we only have variances? Can somebody tell me for extra credit? Why don't we have covariance? Okay, go ahead. Oh, because it's only one variable, one dimensional. Send me a message for extra credit. Thank you for sharing. Okay, so you're only going to talk about variances. Variance of the first cluster, variance of the second cluster. If the variable is more than 2, if you have 2-dimensional, then we could talk about covariance. We don't need covariance here. Any question about this? You're going to be given this. Any question? Okay. The question say, compute the probability that each data point belongs to each of the 2 Gaussian components. Don't forget, in a Gaussian mixture model, okay, we normally have what I call probabilistic assignment. There's overlapping, right? Okay, we want to calculate the probability that a particular data point belongs to a particular cluster. And you know what? A data point can belong to more than one cluster. Now, let's see how we're going to do it. Oh, how are we going to do it? We're actually going to use what I call, expectation maximization algorithm. We're going to start with the expectation. Please pay attention. Oh my God. This is the expectation step. Now, look at that formula. What do you see? In the numerator, you see pi k. What does pi k mean? That is the missing coefficient for a particular cluster. How many clusters do we have? 2. We're going to have pi 1. We're going to have pi 2. You've been given in the question. Look at the pi 1. Look at the pi 1, pi 2. Pi 1, pi 2 equal to 0.5. Do you see that? You've been given. Okay. Now, if you look at that formula now, that is that's a posterior probability formula. You can see what I have in the numerator. What I have in the denominator is just this totality, right? It's just the sum. Summing over cluster, right? That's what it. And you know what? This guy here is actually trying to compute the probability that a particular data point will fall in a particular cluster. Now, but let me tell you this. We're trying to tell you that that's a normal distribution. That n is a normal distribution. Okay? That's why it's called a Gaussian mixture model. Gaussian. That's a normal. Okay? Now, you know what I'm going to do? Please, I need you to pay attention now. Okay? I want to use this particular formula now. Oh my God, it's going to be super easy. Now, you're giving this, right? That's what you're giving, right? I'm going to give you that. I'm actually going to give you that. You know what I want to do right now? For data point X1, how many data point do I have? I'm going to go back. How many data point do I have? Do you see that? 1, 2, 2, 5, 5, 6, 7. I'm seeing something now. Do I need to compute for 2? I have 2 twice. That would be the same value, right? I have 5 twice, right? Go ahead. Which one? Oh, 2.5. Okay. 1, 2, 2.5, 5, 6, 7. So which means there's no data point repeated. Thank you so much. Okay, now I want to start with the point x equal to 1. Please pay attention and tell me, do you know what I've done here? Do you know what I just did here? I applied the normal distribution for data point x equal to 1. What does it mean for that cluster? 2. What is the variance? 1. Plug it in. What do you have? Is there anyone who struggle with that? How we actually got that for data point 1? Is there anyone? Is there anyone who doesn't understand that? Now, take a look at this. I repeated the same. Don't forget that particular data point, we're going to get it for cluster 1, for cluster 2. Does that make sense? Any question? Everything fantastic, right? This is just the normal. Now, after getting the normal, you're going to get this for data point 2. Now, take a look at this now. If I, based on this one, when you are done with this one, when you are done with the particular data point, what did you just get? The normal density for the data point for the two clusters, right? What is the next thing? Then the next thing is to get the probability. How do I come about this one? Okay, where do I get 0.5? I'm coming back here. I'm coming back to use this particular formula. You know that this one is the one I started with, right? Inside that formula, that's the one I started with. So whatever I get, I'm coming to plug it in with 0.5. So take a look at this now. Is there anyone who doesn't understand that? How I got that? Is there anyone? Do you know that one? That is gamma Z11. That means the probability of the first data point be in cluster 1. If I get it for being cluster 1, for being cluster 2 will be easy. 1 minus that, which is this guy here. Any question? And now I got it too. The moment you got the probability of it being cluster 1, the probability of it being cluster 2, because they're going to be mutually exclusive, right? Then I got that. Now I'm done with the first data point. Any question about the first data point? Please ask now. I want everybody to score 100%. If you don't understand now, please ask me question now. Now I'm going to do the same to the second data point. Any question on how I did this? What did I just do? This one is just getting the number. You can see I said 2 for data point 2, given that, okay, you can see I got for the 2 cluster, then I'm actually going to go to the probability now. Oh my God. Do you see the probability now? For each data point, what I'm actually going to do, I'll figure out the probability of it belonging to cluster 1. And if I want to find the probability of it belonging to cluster 2, I'm actually going to subtract it from 1. What am I using? The law of complement. You remember the law of complement? Okay. Now I want to assume you're going to do this to every data point. Okay. You will do that to every data point. You know what I've done? Then you've already obtained the probability of each of the data point belonging to the 2 clusters. Okay. Now the second question. Now, any question before I move to the next one? Any question? Any question? Make sure you come with calculator you can trust. Okay. You come with calculator you can trust. Is there any question? You are good, right? Please ask question now. You pay for the service. Ask me question. Because, exam, you can ask me, you're not going to have opportunity to ask me question. Okay, go ahead. Okay, I allow cheat sheet. Okay, you can write formula down, allow cheat sheet. So I allow like one sheet, double-sided, or 2 sheets, one-sided. Does that make sense? Allow that. Okay. Okay. Now, I want to go to the next question now. Update the means mu1 and mu2 based on the probability computed in the expectation step. You know what we just finished now is just the expectation, right? We now want to come into the maximization angle. Assuming a single iteration and provide all calculation. Now, what I need here, I only need first update. I know there's going to be so many iteration, right? I only need just first iteration. Does that make sense? And if I want to go by that, this is the formula for the update. Do you see the formula? Which means if you take a look at this formula now, do you see gamma? Do you see this guy? The probability you've already found before. Does that make sense? Now, if I want to do that for mu1, this is the mu1. Okay. Where does 0.9999 come from? 0.999, 0.9986. Those are the probability for the first cluster that we got. Okay, don't forget. I'll give you 1 second. Wait a minute. Okay. Now, we actually got this guy. Okay, and we continue to go. Okay, we continue to go for the first cluster. I'm dealing with the first cluster now. Okay, this guy, the first cluster, the first one, or the first one. You can see I'm not using the second one for now. Or the first one, okay, or the first one multiply by the data point, the corresponding data point, then divided by the totality of all those probability for cluster one. Does that make sense? And that is going to give me mu1 equal to that. That's going to give me mu1 equal to this. Then I want to do the second one now for the second cluster. Oh my God. Look out for the second cluster. Finally, I'm actually getting this as a result. And after one iteration, I'm actually going to have that. Please don't go beyond one iteration. It's only one iteration that I want. Is there any question on this? Any question? If you have 100% confidence that you can solve a question like this in exam, can I see your hands up? It's time for celebration. Good job. But you know what? Don't deceive yourself. The moment you know, you need clarification, let me know. Okay? Now, I'm confirming to you 100% there's going to be a question. Do you know what you need? You know what is coming. You know what is going to, you know what you need to practice for? You need to practice for correctness and speed. We only have 50 minutes for the exam. Does that make sense? Okay. Now, we just, one of the major questions. Oh, go ahead. Go ahead. Go ahead. Are you doing what? Oh, how many questions on the exam? I think from what I'm seeing, it's going to be just 3 major questions. 3 major questions on the exam. But you know what? This is one of the major ones. We got 2 to go, right? That's super cool, right? Okay, now I want to go into another one, density base. Okay, I want to go into density base, and I needed to pay attention to the density base. Now, of course, this is easy. They've defined, in a density base clustering, the idea, that cluster data based on, cluster data into cluster based on high density, and then the one with the low density is actually regarded as an outlier or noise. Okay, I needed to pay attention, read. There are 2 major parameters here. We talk about the epsilon, which is a minimal distance, right? And the minimum number of point that can be classified into a cluster. I needed to read your notes. What is the core point? What is the border point? And what is the noise point? But you know what? I'm concerned about this. I'm going to give you data sets that look like these. Okay, giving that, giving this data point 1 to 1, 2, 1, blah, 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 25, 80. Okay, you need to compute the distances between each pair of point and check whether the point can be classified as core point on, I'm going to give you the 2 parameters. Does that make sense? Imagine if I don't give you the 2 parameters, you're all going to get different answers, right? Because you're going to choose a different parameter. But here I'm giving you, let the epsilon equal to 2 and let the minimum point equal to 2. Okay, now I will advise when a question like this come out under the density base, I will advise make sure you use Euclidean distance. You see what I'm using now? Okay, so I started the distance between 1, 1 and 2, 1. Can you see that? Between 1, 1 and 2, 1. I look at the distance, Euclidean distance. This is the way I calculated Euclidean distance, right? Okay, you've done something like this in high school. I remember then when you say x1 minus x2 all squared plus y1 minus y2 all squared, they're going to put square root on that. That's an Euclidean distance. Okay, now you can see here 1.41. And don't forget the minimum point, right? The distance within two distance. Okay, those are say kind of. So you continued like that. You see all of this, and take a look at this guy here. Oh my God. You see all of that, right? Are they within that minimum distance that we just talked about? Okay, so when you do all of this, and there's this particular guy, look at this guy, 74. That is even so glaring. From the beginning, I can even know from my data that that's a noise, right? If you look at 25 and 80, let's go back to the data. Look at the data here. Do you see the data here? Okay, even from without doing anything at all, I know that's a noise, right? Okay, so, and look at the way I answered the question. And I said, identify a core point now. I said 4.11, okay, 4.11. The point within that epsilon equal to 2 and the neighborhood of that, you can see now that epsilon equal to 2 is the neighborhood of 112, 122. I'm actually using the Euclidean distance that I computed. Okay, and I said since they are at least 2 points, okay, then including itself, I said 1 is a core point. Okay, that's a core point. And I said for 2 1, the point, no, I said the point within the epsilon equal to 2 neighborhood of that, therefore is also a core point. Okay, then 2 2 also a core point. Okay, okay, 8 8 now. Okay, I said 8 9 is within its because I compare, you know, when you go back and look at the 8 8 and 8 9, you're actually gonna see from, you know, from what we got. Okay, actually gonna see all of that. Okay, now yeah, but when you get to 2580, I said no other points are within its epsilon equal to 2 neighborhood. Therefore, 25,80 is a noise point. It's looking as if I'm done. That's another major one. That's another major one. Does that make sense? Is there any question here? That's another major one. Okay. So, a question like this, you are likely going to say something like that. Now, I want to go into converse now. Okay. I want to go into converse right now, and I need you to pay attention. Okay. You know, in addition to these 3 questions, I'm going to attach some question with them, like explain or predict. You remember explain or predict? Don't forget, I'm going to also put that, but there's going to be 3 major questions. Now, let's take a look at this. Using the Hessian matrix, you can see that here, I emphasize on Hessian matrix, right? Because there are several ways you can test for convexity. I said, using the Hessian matrix, okay, to test the convexity, and I want hand calculation, you are given the following function. That's a bivariate, right? Compute the gradient of the function. Okay, we want to compute the gradient of the function. Now, how do I compute the gradient of the function? This is how I expect the gradient to be done. You're going to first, if you take a look at, if this is a function, we're going to differentiate with respect to x, and you're going to differentiate with respect to f. And finally, you see my gradient right now? That is my gradient. You have to know how to differentiate correctly. That is my gradient. And after that, I said, compute the Hessian matrix of the function. Okay. If you want to get element in the Hessian matrix, you need to first perform the second derivative. Okay. Take a look at this guy now, the second derivative with respect to s, the second derivative with respect to y, and something you differentiated with respect to x before, you differentiated with respect to y, something you differentiated with respect to y, you differentiated with respect to x, And because of that, you set up your HCM matrix, and this is what we have. Now, let me tell you this. You look at the elements in the diagonal. Can you see that? Element in the diagonal, 6 and 10. That's a positive definite, right? And that's a positive definite indicates that that's a converse. Okay? So you can see, or if you also want to look at the determinant is going to be positive here too. 6 times 10 is 60. 60 minus 4. Okay, that's a positive one. And look at the element in the diagonal 6 and 10. They are all positive, and it means a positive definite. Okay, so take a look at that, how this is done. Okay, now because I see half time, I'm actually gonna say this. Or maybe I should stop. Maybe I should just stop here. But you know what I'm gonna walk you through on Wednesday is still gonna be, because there's gonna be additional question under the converse, where in the assignment I remember I asked you to investigate square root of x, exponential raised power x. But I don't want you to use HCM matrix anymore. Okay, and I don't want you to use second derivative. Okay, but I want you to use inequality. You know that inequality where we have the weighted function. Okay, where you have something like this. Here you have f of x, x lambda 1. You remember this guy, plus 1 minus lambda 1, 1 minus lambda 1, x. Do you remember this one? Less or equal to lambda 1, which is going to be a weighted sum. Okay, f of x, okay, plus 1 minus lambda, 1 minus lambda. Okay, so 1 minus lambda f of x or something. Okay, so this is what I'm going to walk you through on Wednesday. Now, let me tell you this. I just reviewed 3 major questions in this exam. Okay, but there are other 2 that will be an attachment, because in the question where I asked you to use HCM matrix, I'm still going to ask another question where I'm actually going to say use that inequality. Okay, investigate whether s squared or square root of s or exponential raised to power s, investigate whether it's a converse function. Okay, you can check your notes on that. Okay, so then maybe here, in addition to question number 2, maybe after asking all these ones, I'm actually maybe C part of this may be okay, so maybe C part of a particular question may be explain, maybe I gave you some kind of examples and I said, what is the intention here? Is it to explain or to predict? That's all about that exam. I want you to have confidence into that exam. You deserve to score 100% in that exam. Okay. Is there any question for me? Go ahead. Yeah. So what I mean, wait a minute. I'm gonna do something now. I'm gonna show by example now. This is what I mean. Let's say, for instance, you want to come to exam with this. I'm just assuming it should be just 1 page here, 1 page here. Does that make sense? Okay, just one side. Or if you want to come with only this one sheet, this side. Does that make sense? That's what I mean. Yeah, that's what I mean. Okay. You all know this exam is going to send that around to explain or predict. I'm going to put some research question where I'm going to say, okay, what is their intention here? Is it to explain or to predict? You know, we've done that, right? Okay. So, and when I'm actually going to say you should tell me the reason. You don't just choose, say, to explain or to predict. You also need to provide the reason. Does that make sense? Why you believe so. Okay. And before you know, I think what I want you to work on is working on your accuracy and time. You know, before you know, look at, we just started this lecture now. Look at time now, it's flying. You got to know time is flying. And I remember when I was in college, what I normally do, I think I normally write exam before exam. You know what you can do to yourself, okay? You can just write those questions out and don't look at the answers and time yourself. Time yourself. Does that make sense? Time yourself, do it and look at the time and look at your accuracy. I normally use this example to my student when I was in Africa, because in Africa I like watching Mike Tyson. Does anybody know Mike Tyson? Oh, okay, you know that guy. Now I remember then I said I used to tell my student whenever Mike Tyson won or any boxer won, I said this guy did not win here. He won during the training. Does that make sense? When you come to exam and you perform, okay, you did not actually perform. That your performance did not start in the exam. It started when you were practicing. So practice is very, very crucial, because when you are practicing, when you are on your own practicing, you'll be able to know the mistakes that you may make. But it is very, very dangerous to make mistake in exam. The time is going to be flying. So whatever mistake I want to make, I'm actually going to make that before I set my foot into exam hall. Does that make sense? And this is what I used to tell students whenever you are coming to the exam. Don't come with a difficult mind. Come with the mind that I'm going into that exam to score more than 100%. That's what I used to tell myself. Going to that exam, because you have to start with belief that you can do it. If you don't believe you can do it, it may be impossible task for you. Who tells you can't score 100%? Of course you can score 100%. Because if you lose any of the points, that point will not be added to somebody else. You've lost that point forever. And that's why you need to be able to maximize your points. I want to get this point. Okay? So maybe and don't listen to stories. I hate stories. You know, maybe before coming to this class, some people that have taken a class like this before, and they say, oh, that class is going to be tough. And you know what I used to tell myself? If some people are saying it's going to be tough, I'm going to tell myself it's not going to be tough for me. Even though I know maybe under real condition, it's tough. That's why I used to tell people around me. This is the way I see life. At times, I know statistically, life can be complicated and life can be simple. But you know what I normally tell myself? No matter what nature life poses, okay, it just requires me to take my time. You know what I used to tell life? I will figure you out. That's what I used to tell life. I know it's difficult, but I'm not going to agree. I'm not going to admit. I will never admit. I will never. I'll give it. I'll say, okay, I'll figure you out. Just take my time. So if I were you, sit down, do what you're supposed to do on your own, come to this exam with the mind that you're actually going to score 100%. Let me ask this question. What is it going to take from us if everybody score 100%? That's how I used to tell myself, like, why is it so difficult? We can score 100%. We can all score 100%. And that is what the university wants. They want everybody to score 100%. They don't want anybody to lose points. But you know why we lose points at times? Maybe because of distraction. Maybe because we got a lot of things where, that come our ways, I remember we used to have unpredictable event at times. I was to have a meeting, or maybe was it not on Friday or on Thursday with some of my TA. Oh, you're my TA, right? You attended the meeting, right? Thank you so much for asking. You know, I was to have a meeting maybe in an hour's time. I just got a call for my daughter's school. She was throwing up that I have to come immediately. And I needed to meet some of my TAs for very crucial meeting. So how am I going to do it? I was having that meeting inside my car on the way to my wife was sitting beside me. And my wife was like, do you love your job more than your daughter? I said, but we're on the way to the hospital. And I told my wife, you know what? Our daughter is going to be fine. And when we go to the hospital, and when we get to the school, we pick her up and she's fine. So I told you, she's going to be fine. But it's expected, she has to what's going on here? So at times you could find yourself in the middle of a very difficult situation, but with a statistical mind, you will figure it out. Is there any question before I go? Okay, come to my exam with an excellent grade. Make sure you all stay safe and have a lovely day. Bye for now, everyone. Yeah, go ahead.